All right, this next example 3. Take a look at this. We've got something that's going to be integration by parts. So first step for any of these problems is to replace your infinities with some sort of parameter and use a limit to do the business of going to infinity, or in this case also negative infinity. So I'll go ahead and say as r goes to infinity, and then I'll just put a negative sign on that r at the bottom so that we go ahead and that's able to take care of both positive and negative infinity in one swap, so that's good. X e to the x dx. Now this is integration by parts. So u equals x, let's do. Then du is dx. For the choice of dv, let's let dv be e to the x dx. Then the integral of that is e to the x. So with that choice in mind, we can continue here. Now each and every time until essentially the very end, we're going to have this limit. So let's just copy that limit, have that right in front, and then we'll run integration by parts here. So this will be u times v between negative r and r minus the integral from negative r to r of e to the x dx. Of course, this integrates to, again, I guess we can copy almost all of this. Right there. Integrating this, we'll just have e to the x between negative r and r, and we don't really need those two evaluation bars at this point because we're going to plug it into each. So I guess we can shorten this a little bit. There we go. So evaluating this with our limit, plugging in, we'll have r e to the r minus, and in fact notice here that we can simplify this. We can write this as x minus 1 e to the x. So let's think of it written like that. Makes it a little bit easier to plug in, less writing. So this would be r minus 1 e to the r minus negative r minus 1 e to the negative r. All right, this term here, the second term, it is technically of the form negative infinity times e to the negative infinity. Well, as e to the negative r, as r goes to infinity, this goes to 0. So this term is going to 0, but this term here is going to negative infinity. Well, but it's double negative, so I guess positive infinity. Regardless, it's infinity times 0. It's that indeterminate form. Well, no matter how large of a degree polynomial we have, in this case it's not a very large degree, it's only first degree polynomial, but even if I had r to the 10 billion, or to the 1 billion, well, 10 billion is 10 to the 10, if I had something like that, an insanely large power, it doesn't matter. This will win. And this will always win. So this is going to go to 0. One way you could also show this is by using L'Hopital's rule. You could go ahead and let's factor out this this negative 1 here. So we just have a positive r plus 1 e to the negative r. And if we write that as a fraction, this would be r plus 1 over e to the r. So this would become r plus 1 over e to the r. And if you think about the limit of this, as r goes to infinity, we get infinity over infinity, which means we can use L'Hopital's rule on this. So if we use L'Hopital's rule, we'll have 1 over e to the r, which goes to 0. So you may need to break out L'Hopital's rule for some of these limits if you're having trouble. So just justify that. So this whole term goes to 0. This term here, this term's going to infinity. This term is going to infinity. That's not an indeterminate form. That limit just equals infinity. So we have infinity plus 0, so this limit is equal to infinity, which means that the integral, the improper integral, diverges.